Hi everyone, I am Yuhan from Rice University. Today I will be talking about our work on adversarially robust quantum state learning and testing. Before I begin, I want to say obviously this is a quantum paper, but at the same time this is also not a quantum paper because a lot of the ideas and techniques are inspired by classical statistics and algorithms. So I will start with the quantum background, then I will describe our problem setup, then I will go over our main results, and then finally I will discuss the ideas improving our results, which includes the lower bound part and the design of the algorithm. So we mainly study the problem of learning information from quantum states. This is a very fundamental problem in physics and quantum computing, because imagine if you run a quantum algorithm or a physicist performs an experiment, it generates some quantum state. And we need to know about the properties of the state. However, the law of quantum mechanics states that we cannot directly know exactly what the state is. We must use measurements to learn about the state. Um, However, another problem is that measurement usually collapses the state, and we only obtain a random classical outcome that only tells some partial information about the state. So how should we do this? The answer is to use more copies. So one way that we can learn about the state is to uh, measure each copy independently using some measurement. Formally, this type of uh, approach is called single copy and non-adaptive. So, which basically says, okay, we have n copies of the state, and then we can decide a set of measurements to apply to those states, and these measurements could be different. So we gather a set of outcomes, and based on the outcome, we can run a post-processing algorithm that tells us about the information of the state. So this is very similar to learning about unknown distributions using some number of samples. And of course, I want to mention there are more powerful and advanced methods, but this kind of method is simple to implement in practice, and this setup will be the main focus of our work. In reality, though, uh, like quantum computing faces a very important challenge, and this is noise. Um, so, as an example, when you when you prepare the state, it could end up with a different state that you hope for. So this is called state preparation noise. And noise could also appear in the measurement process. So even though your state might be correct, when you apply the measurement, it may not produce the desired outcome that you hope for. So together, these noise are often referred to as spam noise. So we want to argue that it is often very difficult and sometimes unrealistic to make assumptions on these noise, because those errors can often occur very unexpectedly, and they can actually depend on the measurement. So it makes it very difficult to come up with an exact mathematical formulation about what the noise could be. Moreover, besides all the physical factors, there could also be malicious human factors. So imagine an adversary could hack into your system and make some damage to your algorithms. So a very important question in practice is that when we have little knowledge about the structure of the noise, can we robustly learn about the unknown state in this worst case scenario? So now I will describe the problem setup. So first, I will start with some notations. Uh, for an n-qubit state, we say that the dimensionality is 2 to the n, which is denoted by d. And in general, a quantum state can be described by a d by d positive semi-definite Hermitian matrix with trace of 1. So this is an illustration. And for those who are not familiar with quantum, I want to say that this is just a mathematical generalization of discrete distributions. Because if you put a discrete distribution over d elements on the diagonal entries of a matrix, this is exactly a valid quantum state according to this definition. So now I will introduce some metric for the space of quantum states. So we mainly consider the Schatten p-norm. So for a Hermitian matrix A, the Schatten p-norm is simply the LP norm of the spectrum. And at some important special cases, when p equals 1, this is called the trace norm. And the trace norm of the difference of two quantum states is called the trace distance, which generalizes the L1 distance between two discrete distributions. Another important special case is the case when p equals to 2. So this is often called Frobenius norm or Hilbert-Schmidt norm. So for non-quantum audience, we will often use the Dirac notation, and this Dirac notation with brackets simply means nothing more than a complex vector. And if the bracket points to the left, it means the conjugate transpose of that vector, which is a row vector. So now I will define the problem of quantum state learning and testing. So first we have a desired error metric, which is the trace distance. The problem of quantum state learning, or tomography, is to learn the full state description with epsilon error. So we have a state rho, which is unknown, and we want to obtain an estimate rho hat that is close in trace distance. Another problem that we are interested in is testing. The goal is to test whether the state is the desired one or it is epsilon far from it. So in practice, we often want our algorithm to generate a specific state sigma. So this testing problem would enable us to determine whether the unknown state is actually this desired state or not. So I want to also say that since quantum states generalizes discrete distributions, so these two problems also generalizes the problem of discrete distribution learning and testing. So we want to do these tasks under noise. So we need to define our noise model. So simply put, we assume that there's an adversary that could change gamma fraction of the measurement outcomes. And the adversary can be adaptive to your measurement strategy. So more precisely, let's say we have designed a set of measurements that we want to apply for the copies, and we are supposed to obtain some set of outcomes. We assume that an adversary could step in. The adversary knows the state and the measurement we are choosing, and also it can read the entire set of outcomes. And then based on all those information, the adversary can freely choose gamma fraction of the outcomes and arbitrarily change it to anything else. Then we would take the corrupted samples and then apply our processing procedure to learn about the state. The main question is, under this model, can we reliably learn or test an unknown state in this almost worst case scenario? So obviously, learning under noise is an important problem. People have studied this before, but uh, we will later show that our noise is actually strong, very strong in some sense. So one type of noise people have considered is I'm I'm phrasing it as bounded span noise, which essentially says that the effect of state preparation and measurement noise will shift your outcome distribution by a total variation distance of at most gamma. And also this shift in the outcome distribution or noise can actually are allowed to depend on each measurement. So under this noise model, we can actually design a tomography algorithm that learns any unknown state with an error of gamma, which is information theoretically optimal. So I want to say that our noise model, the gamma corruption model, is actually stronger because an adversary can simulate the effect of bounded span noise by changing roughly gamma fraction of the outcomes using a well-known coupling argument. So, so now I will introduce the results. So the main question is, okay, under our stronger noise model, can we obtain a similar performance? So we start with the lower bound on the problem of quantum state testing. We show that there exists a quantum state such that no algorithms using non-adaptive single copy measurements can tell whether a state is equal or epsilon far from the state, and the epsilon has to be at least gamma times square root d. So this is a very bad news because recall that the trace distance between quantum states are at most a constant. And also, the dimension d is exponential in the number of qubits. This means that corrupting an exponentially small fraction of the outcomes would ruin all algorithms using non-adaptive single copy measurements. So this is another proof that our noise model is much stronger than the bounded span noise, and as we can see, it can create a much worse damage to the algorithm. So it seems that it's a very pessimistic result, and it seems that we are doomed, and it's not possible to robustly learn any unknown state. But I want to say that we're not quite doomed because the state that achieves the lower bound is defined as identity divided by d, which is called maximally mixed state. The physical interpretation of this is that it's just pure noise. I mean, of course, there are cases where it's useful, but most cases it's probably not. So in practice, the states that people care about often have stronger structures. So one example is the state may have low rank structure. So if the state has a rank of R, then an immediate corollary from our previous lower bound is that the error for testing must be at least gamma times square root R. So can we achieve this error lower bound? So the answer is positive. So with sufficiently many copies, we can actually design a tomography algorithm that actually learns the entire state, uh, the full state, that basically achieves this optimal error. So this is a very good news because in many quantum algorithms, we would use rank 1 states. And for those states, our result basically says we can achieve a dimension-independent error. And we want to mention that the lower bound of gamma is like information theoretically limit for all algorithms, even for the strongest ones that we have not introduced here. So this sends a very important message that if we have structural information about the state, it can actually help us to learn the state robustly. So now I will introduce the idea in the proof. So why is it not possible in this case? For those of you who are familiar with robust statistics, this may be surprising because in some cases, say for Gaussians, we can actually achieve an error of gamma which is dimension independent, even though we are actually trying to estimate a higher dimensional distribution. But in our case, more precisely single copy non-adaptive setting, it's not possible. So the reason is that the high level reason is because measurements themselves are inherently constrained. Recall from our previous description, when we apply a measurement, we only receive partial classical information about the state. So this means that if your algorithm wants to learn the state accurately, it must be sensitive to changes in the outcomes. So having a large sensitivity would often imply your algorithm would be less robust. So how to argue this concretely? We basically construct a set of states that is epsilon far from our reference state, which is the maximally mixed state. So we basically design a binary hypothesis testing problem. When we apply some measurement on these two cases, to distinguish them, we need that the outcome distribution of the two cases must be sufficiently separated. So what an adversary can do here, it can take the outcomes from one of the cases and perform some corruption, and after this corruption, the adversary can make the new outcomes look very similar to the other case, which makes it hard for your algorithm to distinguish. What we show is that the adversary only needs to change epsilon over square root d fraction of those outcomes to make it impossible for any algorithm to distinguish the two cases. So by rearranging the terms, we immediately prove our lower bound, which says that epsilon must be larger than gamma square root d. So now we'll talk about the algorithms. So we use ideas from robust statistics. So first, I will introduce a standard way, a standard algorithm for tomography. Um, so we apply a measurement such that the outcome would be distributed over the unit complex sphere, and the distribution can be related to the unknown state in this way. So essentially, the unknown state can be written as the expectation of the projection matrix. So a standard non-robust algorithm would simply estimate this mean using the empirical estimate. So to make it robust, we just need to find a way to robustly estimate this mean. Or also equivalently, this can also be viewed as the covariance matrix of this outcome vector. So how should we robustly estimate the mean? So we get gamma corrupted samples from an unknown distribution D, and as an example here, we have some set of good samples and maybe bad samples. Ideally, we want to throw away all the bad ones, which are the red points, and only keep the green ones. But this is not possible. So we take a step back. Instead of trying to pinpoint for each data whether it's good or not, we try to find a good subset of the samples, which may contain a small portion of bad samples, but they can give us a good estimate. So as an example, this set of samples could be considered as a good set because it contains only one bad sample, and it seems, at least in the picture, that the bad sample is not actually doing much damage to the mean estimation. So So now the question is to how to find a good set of samples. The idea is to define a criteria or certificate for what we mean by a good subset. And the criteria should also satisfy that any subset which satisfies the criteria, the empirical mean over the subset should be an accurate estimate of the true mean, even though the subset may contain bad samples. So once we have this criteria, we can just perform a brute force search. So, for example, we may start with taking this set, and maybe we decided that it's not a really good set of samples, so we look for another set. It's also not very good. And then we may end up with a set that satisfies our criteria, and we just output the empirical mean over the set as our estimate. Of course, we may end up with a different set, but as long as it satisfies the criteria, we are happy with it. So how should we design such a criteria? So as an example, we consider estimating the mean of a distribution with covariance bounded by the identity matrix. So the criteria is actually very simple. Because the distribution has bounded covariance, we simply look for a subset of samples that has bounded empirical covariance. And we can show that the empirical mean of such a subset would be close to the unknown mean, and the distance is square root gamma in L2 distance. Moreover, we can show with high probability that any gamma corrupted samples would contain such a good subset. So we can actually find a good subset. And we don't have to worry too much about the time efficiency regarding the brute force search, because it can be made time efficient using either filtering or sum of squares technique. So we can apply this algorithm to tomography. Recall that we get samples on the unit sphere, and we can further bound the covariance of this matrix. So we are kind of treating this matrix as a vectorized version. So it actually has bounded covariance, and as a result, using the previous algorithm, we would obtain an estimate rho hat that is square root gamma close in Frobenius distance. Then using Cauchy-Schwarz, this will translate to gamma times square root d in trace distance, and it can also be improved to gamma square root r if the rank is r. So we're almost there, but the algorithm is not achieving the desired error with respect to dependence with respect to gamma. So ideally, we want to improve the error in Frobenius distance to gamma. So how should we do it? So we need to take advantage of more structural information about our distribution. Recall that our distribution is actually very well structured. It's on the unit sphere, so you should have bounded higher order moments of any order. But our previous algorithm only used the fourth order moment. So we need a better certificate for the good samples. So it turns out that the certificate that's good enough for our purpose is hypercontractivity, which essentially requires that the any degree 2 polynomial of our outcome vector should have bounded higher order moments. And it is sufficient to just choose the order h to be roughly log 1 over gamma. And to make the algorithm more efficient than just brute force search, we can actually use the sum of squares technique, which essentially helps us to approximately find the subset that satisfies the hypercontractivity condition, and which in turn gives us a desired estimate with good accuracy. So the number of samples that we need is pseudo-polynomial, which is d to the power of log 1 over gamma. So this concludes our results. So some future directions include, first of all, improve the sample complexity to polynomial in the dimension, and also to study adversarial robustness for stronger measurements, more precisely adaptive and entangled measurements. And finally, we are also interested in designing a truly efficient algorithm for states that have even stronger structures. By truly efficient, we mean the complexity should be polynomial in the number of qubits. So thank you very much. Please check out our paper on arXiv.